Hello and welcome to Think Tech. I'm your host Shivam, and today we have an exciting and in-depth topic lined up. We'll be taking a deep dive into Apache Spark, the powerful distributed computing system for big data processing. In this episode, we'll explore the core concepts and the inner workings of Spark. So let's roll up our sleeves and delve into the world of Apache Spark. To start, let's introduce Apache Spark, a powerful and versatile distributed computing system that has become the go-to choice for handling immense volumes of data with unparalleled efficiency. Spark's core design principles revolve around speed, making it a perfect fit for data-intensive applications that demand real-time or near real-time processing capabilities. Unlike traditional data processing frameworks like MapReduce, Spark takes a revolutionary approach by leveraging the power of memory. By keeping data in memory, Spark minimizes the need for frequent disk read-write operations that were the bottleneck in earlier data processing paradigms. This memory-centric architecture allows Spark to swiftly access and manipulate data, drastically reducing processing times and improving overall performance. As a result, complex data processing tasks that once took hours or even days can now be accomplished within minutes or seconds, enabling organizations to make critical decisions and gain insights at a pace previously unimaginable. Moreover, Spark's efficiency doesn't stop at speed alone. It also offers ease of use and accessibility. With its intuitive and user-friendly APIs in popular programming languages such as Scala, Java, Python, and R, developers of various skill levels can quickly grasp and harness its capabilities. This accessibility has contributed to Spark's widespread adoption across industries, attracting a vibrant community of open source developers who actively contribute to its ongoing growth and innovation. Now let's delve deeper into the architecture that makes Apache Spark a highly efficient and scalable data processing powerhouse. At the core of Spark's architecture is the master worker model, which enables it to efficiently handle massive datasets across distributed clusters. In this model, the central coordinator, known as the driver, plays a pivotal role. The driver program is responsible for orchestrating the entire data processing workflow. It receives the application code and data from the user, plans the execution of the tasks, and monitors the progress of the job, acting as the brain of the Spark application. The driver ensures that the data is processed in a coordinated and optimized manner. Complementing the driver are the distributed nodes called executors, which form the worker nodes in the cluster. Each executor is responsible for carrying out the task assigned to it by the driver. By dividing the workload into smaller units, Spark achieves parallel processing, where multiple tasks can execute simultaneously across multiple executors. This distributed execution enables Spark to handle large-scale data processing with impressive speed and efficiency. Additionally, Spark's architecture is fault-tolerant, ensuring the resilience of data processing even in the face of node failures. When an executor encounters an error or crashes, Spark's driver automatically reschedules the failed task on another available executor, preventing data loss and maintaining the overall job's integrity. Furthermore, Spark's architecture allows it to be deployed in various cluster management systems like Apache Hadoop Yarn, Apache Mesos, or its standalone mode. This flexibility empowers organizations to integrate Spark seamlessly into their existing big data systems, making it a versatile and adaptable solution for diverse data processing requirements. So in summary, Apache Spark's master worker architecture, with its driver and executor components, forms the backbone of its lightning fast and robust data processing capabilities. By efficiently distributing tasks across the cluster and providing fault tolerance, Spark ensures that even the most extensive data processing jobs are completed efficiently and reliably. As a result, Spark has become a cornerstone technology for businesses seeking to harness the power of big data and gain valuable insights in real time. In the vast landscape of big data processing, a common and crucial comparison arises between MapReduce and Apache Spark. While both are designed to handle large-scale data processing tasks, Spark's unique features give it a significant edge over MapReduce in terms of performance and user-friendliness. One of the key differentiators in Spark's innovative approach is of caching data in memory. Unlike MapReduce, which relies heavily on disk read-write operations, Spark keeps frequently accessed data in memory, reducing the I/O overhead. This in-memory processing capability grants Spark a substantial advantage, resulting in significantly faster data processing times. As a result, Spark is well suited for iterative as well as interactive queries, where data needs to be accessed and processed multiple times. These iterative tasks, which would be time-consuming in MapReduce due to repeated disk reads, are executed with remarkable efficiency in Spark, making it the preferred choice for machine learning, graph processing, and real-time analytics applications. So while MapReduce laid the foundation for distributed data processing, Apache Spark has emerged as the revolutionary successor that pushes the boundaries of speed, performance, and usability. With its in-memory data processing and parallel execution capabilities, Spark is a clear winner for handling iterative algorithms and interactive queries, opening new avenues for real-time data insights. Its developer-friendly nature has contributed to its widespread adoption and solidified its position as the go-to solution for organizations seeking powerful and efficient big data processing. Now let's talk about a very important concept in Spark, that is of partitions. The concept of partition lies at the heart of Apache Spark's ability to handle massive datasets. When the data is ingested into Spark, it is divided into smaller, manageable chunks known as partitions. These partitions are the building blocks of distributed data processing, as they enable Spark to perform operation on each partition independently and concurrently across the cluster nodes. By breaking down the data into partition, Spark achieves parallelism, a crucial factor in optimizing data processing performance. Each partition can be processed by a separate executor on different cluster nodes simultaneously. This parallel processing greatly reduces the overall processing time, enabling Spark to tackle complex data processing tasks efficiently. Moreover, the number of partitions and their size can be optimized based on the characteristics of the data and the available resources in the cluster. Spark's flexible partitioning approach allows users to fine-tune the level of parallelism to suit their specific data processing requirements. With the right partitioning strategy, Spark can effectively utilize the available resources and ensure that each node is fully engaged in processing, avoiding any idle time and maximizing cluster performance. So in conclusion, the concept of partitions is a fundamental and a powerful aspect of Apache Spark's architecture that enables it to achieve remarkable data processing performance. By breaking down data into smaller units and processing them in parallel across distributed node, Spark optimizes its processing capabilities, making it a top choice for handling large-scale, data-intensive workloads in various domains. In the dynamic world of Apache Spark, three essential data abstractions have emerged to empower data engineers and analysts in processing and manipulating vast datasets. Those are RDD, Dataframe, and Dataset. RDD, which stands for Resilient Distributed Dataset, serves as the foundational data structure in Spark. It represents an immutable distributed collection of objects spread across the cluster nodes, enabling fault-tolerant and parallel data processing. RDDs provide developers with fine-grained control over data manipulation, making them well-suited for complex data processing scenarios where low-level transformations are required. Building upon the foundation of RDDs, Spark introduced data frames and data sets, which offer higher level of abstractions with additional benefits. Data frames are distributed collections of data organized into named columns, much like a table in a relational database. This tabular representation allows Spark to leverage the power of structured query optimization techniques, enhancing its performance in querying and processing structured data. Data frames also come with an optimized Catalyst query optimizer, which intelligently transforms the high-level code into efficient execution plans, assuring faster data processing. Similarly, data sets extend the capabilities of data frames by introducing type space, object-oriented programming interfaces. By combining the benefits of RDDs and data frames, datasets enable the best of both worlds, strong typing and high-level abstractions. This results in more concise and expressive code with the added advantage of compile time safety, reducing the chances of runtime errors. So the introduction of data frames and data sets have significantly contributed to Spark's user-friendliness and efficiency. Developers can now leverage the expressive power of SQL-like queries, while the underlying Catalyst optimizer ensures efficient execution. Moreover, the rich ecosystem of Spark libraries and connectors seamlessly integrate with data frames and dataset, making it easier to work with various data sources and formats. So in conclusion, the trio of RDD, data frame, and dataset forms the backbone of data processing in Apache Spark. While RDDs offer granular control and fault tolerance, data frames and datasets introduce high-level abstractions with schema information and type safety. Next, let's talk about actions and transformations in Apache Spark. In Spark, actions and transformations are fundamental building blocks that drive the data processing workflow. Transformations, as the name suggests, are operations that take an existing dataset, apply specific transformations to it, and produce a new dataset as the output. These transformations are performed in a lazy manner, meaning they are not executed immediately, but rather Spark builds a logical execution plan, optimizing it for efficiency. This approach allows Spark to defer the actual execution until an action is triggered, minimizing unnecessary overhead and maximizing performance. This is what is known as lazy evaluation in Apache Spark. Transformations play a crucial role in shaping and refining data, enabling operations such as filtering, mapping, aggregating, and joining datasets. On the other hand, actions are operations that kickstart the execution of Spark's logical plan and trigger the actual computation. When an action is called, Spark evaluates all the previously defined lazy transformations to produce a result or return data back to the driver program. Actions are responsible for initiating data processing and delivering final outcomes, such as saving data to external storage systems, collecting results to the driver, or performing aggregations to generate summaries. Unlike transformations, actions are eager operations that trigger the evaluation of the entire computation graph, leading to the execution of the logical plan and the realization of the data processing tasks. By distinguishing between actions and transformations, Spark ensures a clear separation between the logical planning phase and the actual execution phase. This separation allows Spark to optimize execution plan thoroughly, minimize data shuffling, and exploit parallelism effectively. It also provides developers with a fine-grained control over the flow of data processing, enabling them to design sophisticated and efficient data workflows tailored to the specific requirements of their applications. In a sense, the careful interplay between the actions and transformations empowers Apache Spark to handle large-scale data processing tasks with impressive speed, scalability, and reliability. Now let's talk about another very important concept in Spark, that is Spark Session. The Spark Session serves as a vital entry point to the world of Apache Spark, providing users with a unified and streamlined experience for harnessing the full potential of Spark's capabilities. This crucial component consolidates the functionality of earlier Spark contexts, such as Spark context, SQL context, and Hive context, into a single cohesive interface. By doing so, it simplifies the process of interacting with Spark, making it more accessible to developers and data engineers. One of the primary roles of Spark Session is resource management. It acts as a smart resource allocator, efficiently distributing computational resources across the cluster nodes. The Spark session optimizes resource allocation, ensuring that each task is allocated an appropriate amount of memory and processing power based on its requirements. This resource management ensures that application runs smoothly and efficiently, avoiding resource bottlenecks and maximizing cluster utilization. Another key responsibility of Spark Session is handling various data sources. It seamlessly integrates with a wide range of data storage systems, including distributed file systems, databases, and cloud storage services. The Spark Session provides APIs to read and write data from these sources, making it easy to ingest, process, and store data without the need of complex configurations. This data source flexibility enables Spark to interact with diverse formats and structures, making it a versatile tool for big data processing. So in conclusion, the Spark session is a fundamental component that streamlines the Spark experience and enhances its performance and capabilities. By offering a unified interface, it simplifies interaction with Spark, making it more user-friendly. Its resource management ensures efficient utilization of cluster resources, and its compatibility with various data sources allows Spark to handle diverse data formats seamlessly. With the Spark session as the central orchestrator, user can harness the full potential of Apache Spark, empowering them to perform complex data processing tasks and gain valuable insights from their big data with ease. Moving forward, let's delve into the internal execution mechanics of Spark jobs, which rely on the concepts of stages and tasks. A stage in Spark refers to the collection of transformations that share the same data dependencies, allowing them to be computed together as a single unit. On the other hand, task represents the individual unit of work within each stage, executing specific transformations on the partition of the data. Spark's intelligent scheduler efficiently organizes these tasks, optimizing their execution by considering factors like data locality, task dependencies, and available resources. This careful orchestration ensures that data processing is carried out in the most streamlined and parallelized manner possible, enabling Spark to handle large-scale data processing workloads. At the core of Spark's powerful execution model lies the representation of computation as a directed acyclic graph. The DAG scheduler plays a pivotal role in optimizing the execution flow of data processing tasks by breaking them down into a sequence of stages with clear dependencies, enabling efficient parallelization. Additionally, the DAG scheduler ensures robustness by tracking the lineage of data transformations, allowing Spark to recover from failures and recompute lost data if necessary. This fault tolerance capability enhances the reliability of Spark, making it a resilient and dependable solution for large-scale data processing, where data integrity and continuity are of utmost importance. Lastly, understanding the different execution modes in Apache Spark is essential for optimizing its performance and resource utilization based on specific use cases. The three main execution modes in Spark are client, cluster, and local, each serving distinct purpose and catering to different scenarios. In the client mode, the driver program runs on the client machine from which the Spark application is submitted. In this mode, the client machine is responsible for initiating and controlling the Spark job, while the cluster nodes execute the assigned tasks. This mode is particularly useful during development and debugging, as it allows developers to interactively monitor and manage the application's execution, making it easier to identify and resolve issues in the code. On the other hand, in cluster mode, the driver program runs on one of the nodes in the Spark cluster. The client machine, after submitting the application, disconnects from the cluster, and the Spark job continues to execute on the cluster node independently. This node is preferred for production environments as it maximizes resource utilization by freeing up the client machine once the job is submitted, enabling it to focus entirely on data processing without client overhead. Lastly, the local mode is ideal for testing and development on a single machine. In this mode, Spark runs as a single Java process on the local machine, simulating a distributed cluster within the same system. While it is not suitable for processing large-scale data, the local mode provides developers with a convenient and a quick way to experiment with Spark functionalities without the need for a full-fledged cluster setup. Selecting the appropriate execution mode depends on the specific requirements of the Spark application and the available resources. In development and testing phase, the local mode allows rapid iterations and ease of debugging, while the client mode enables interactive control. In production scenarios, the cluster mode ensures optimal resource utilization and high performance data processing across the distributed cluster. And there you have it, a comprehensive and in-depth exploration of Apache Spark. I hope this episode has given you a solid understanding of Spark's fundamental concepts and how it revolutionizes big data processing. Remember, technology is a vast ocean of knowledge and there is always more to learn. Stay curious, stay informed, and keep thinking tech. Thank you for joining me on this episode of Think Tech. If you have any questions or feedback, feel free to reach out. Stay tuned for our next episode where we'll delve into another exciting tech topic. Until then, this is Shivam signing off. Have a great day.